All right. So I suppose I'm live, and I'm hoping everybody's seeing the presentation there. So my name is Ezekiel Buchheit. I go by Easy, and I am work for the Last Mile org at Amazon. So I'll give you a quick introduction about the Last Mile org and about myself here. We're going to talk to you today about the Amazon States language and how we utilize it in our app. You'll see me looking down here at my notes as we go, so I apologize for that. And why we chose to use the Amazon States language. So for this particular talk, there's no expectation for you to have any familiarity with Amazon States language, nor is there any expectation that you'll have any familiarity with like using state machines inside of an app for that matter, or anywhere else. We're going to go through kind of all that. This is intermediate to beginning. So quick background on myself. I've been an Android developer since back in the Gingerbread release years. I started out kind of bouncing around the startup community in Austin, Texas, where I'm from. And so for several years, I mean, I've been with startups at all stages of the growth, from seed to sale, a lot of success, a lot more failure. But I've kind of touched it all and did that for about 5 years. And then in 2015, I joined Amazon in Last Mile. And joined then what I'd call the rapid ascension of kind of the whole Last Mile org and the Flex app, which is what we're going to talk about today specifically. So it was already large, but it was growing rapidly. At the time, there were probably 10 Android developers on the app, and the app was large enough that, or small enough that any given app developer could know every inch of the code base. So that's when I joined back in 2015. So to give you a little bit of background on Last Mile org, so that is the arm of Amazon that is concerned with getting packages from the local warehouses to your door. So we've got our warehouse here and my phenomenal fancy presentation here. The Amazon Flex app sits in the center. We get it to your house. So if you've ever been on Amazon.com, you've ordered a package and you've seen delivery by Amazon and like your order history, that means the Last Mile org was involved in it. So this is a full scale worldwide operation. It's got a multitude of levers and gears. But we're going to focus for the sake of this talk just on the Flex app itself, the center portion of this. So the Flex app, which we have in both Android and iOS, is the delivery app that the transporters, and the transporters are your package delivery drivers, interact with. So we support, like I said, both Android and iOS, and this is an enterprise level logistics app. That's key to understand. So it needs to work in all conditions, not simply the ideal condition, whether this means in a degraded or non-existent internet access or, last generation hardware. And regardless of any given condition, the apps need to retain a very high level of performance and integrity, because we can't risk the app failing, mid-delivery. So what we do here as the developers in the Flex team is we keep our transporters happy with a reliable app, an intuitive app, and they in turn, keep our end customers happy by being able to deliver on time. So we're constantly iterating on these apps to improve the experience in all ways. And as we are constantly iterating, we're bringing it to new delivery markets. So in order to help us with these goals, we've had to grow, and we've decided that one of the infrastructure changes we're going to make is to integrate the Amazon States language, as I said, as an infrastructure level in both the Android and iOS apps. So before we get into why and how we did that, I want to take just a brief moment over to talk about scale. And I want to do that just for the sake of context, because it'll help understand why we're making the architectural choices that we're making, and it'll give you an idea of the level of scale that Last Mile is involved in. So I want to say, I think you can describe scale maybe in four broad terms. And each one of them come with their own challenges. So most classically, we can think of scale in sense of distribution. So this is the footprint of the project, both in terms of users and in terms of the user's physical regions. So as the regional distribution radius increases, the actual location from which your users are coming, so do the variety and uniqueness of the challenges that you have to be solved in each one of these regions. So I'll give you a really great example. Mapping and map tiles themselves operate entirely different in the United States versus India versus Japan. So as we've moved into these regions, we've had to solve mapping and map tiles for each one of these sections uniquely and individually. At the same time, as the quantity of users increases, each decision that you make that affects the project grows in risk. So as the risk grows, so does the accompanying risk management. These are all your regression testing. This is your A/B testing, rollout, rollback, kind of all the stuff around it that helps mitigate potential issues within development. So this alone, just the risk management elements of it and that growth, affects the development and delivery velocity itself. And as the number of users increases, so does the numbers of transactions per second your system has to deal with. So now we've got this increased load on the system, and with it, its own set of challenges. A second definition of scale here would be, the importance of your particular code. So illustrated here with the keystone and an arch. So how integral is this to the system? Is this project the keystone on which all the other structures are dependent? And, in the case of this, pushing out a bad build can collect problems across dependent systems and then wash on downstream to your customers. And then we finally have two last elements of scale I want to go through real quick, and then we'll jump into the states language and things that we're doing. And both of these have to do with the size of the code base and with the number of developers and accompanying staff that are working on it. So as the code base increases, and I've lost my speed. As the code base increases, you lose code visibility as an individual developer. Testing takes a lot longer. This is where interwoven dependencies increase. And as they can increase, fragility is introduced and grown. Tech debt increases. Those little temporary fixes, that little patch here and there that is just to kind of move forward until you have time to really work on it, those suddenly become permanent. And then, seemingly simple things like just a consistent UX look and feel across the app can become cumbersome and challenging to work with. And in the case of apps that exist across OSs, this is where parity drift begins. And finally, as the number of people working on a project increases, so increases the risk of miscommunication, miscommunication across individuals, teams, features. So we increase the number of different strange and conflicting architectural approaches. Code quality can vary wildly across individuals and wildly across groups. So I bring this up because any individual app or project may grow and scale in one or any combination of these ways. The Flex app itself is at scale in all of them. And as scale in all of these definitions continues to grow, with it the need to architect not just app-wide solutions, but apps plural and back-end solutions to work with current scaling issues, while at the same time mitigating future ones. So as part of the solution, that's why we've turned towards the Amazon States language. So real quickly, what is the Amazon States language? And so I brought up the landing page here from it, and I'll read this off real quick and interpret it. And so what it is from the landing page is the Amazon States language is a JSON-based structured language used to define your state machine. And it's a collection of states that can do work, such as a task states, or it can determine which state to transition to next, which would be a choice state. It can do things like stop execution with an error that's a fail state, and there's a bunch of other things it can do. So if I were to reword that, I'd say the Amazon States language allows you to define flows, establish contracts at boundaries, and deal with errors in a format, JSON, with which we're all familiar. By having a consistent state machine language, we can separate out the states from the machine itself. That's the benefit of using one particular consistently defined language across the apps. Now what happens is the machine's job is only to interpret a consistent set of rules. Certainly many of us here have worked on a project where a state machine made sense. And, from an architectural standpoint, and then over time, we found that the machine itself became too large and cumbersome, making changes to it because it became so interwoven, became as challenging as everything we were trying to mitigate earlier. By having a really clean separation of the language and the machine executor and interpreter, we can avoid that particular situation. So that's kind of state machines and the Amazon States language, but why would we choose Amazon States language, for an app itself? One of the first choices, one of the first reasons here is, before I get into that, I just want to note that this isn't the catch-all architectural solution for the app. So we were describing scale earlier. We aren't solving all elements of scale with this. This is an element of a larger re-architecturing project. So the details of the actual larger project far exceed what we can get to. So we're just going to focus on this element of it here and what Amazon States language itself does for us. So given that focus, what parts of scale that we described earlier is this helping us to solve and the challenges therein? So this works to mitigate issues in both the size of the code base and the number of people working on it. This is where feature team isolation comes in. So for the size of the code base, it doesn't shrink the code base. Instead, what it does is it removes the need to have knowledge of other teams' work. So this is the visibility issue. You define your state machine to do your work. And if you need to link into some other team's feature, whether it's a provider or receiver of information from somebody else's feature, you simply need to know the data contract. That's that boundaries we said we can define earlier, what they're returning or what they expect to receive. And then you can call into their particular state machines. And we'll get into that in a bit. It'll be a little less cryptic. But by allowing teams to work as individual feature teams, individuals can now have focused domain knowledge rather than needing to have complete app-wide insight. So this also means that new feature integration is vastly easier because machines are self-contained, maintain no permanent internal state, and are independent of each other. We reduce the opportunity for strange code interplay to have a negative effect on the app. That's that last bit of kind of feature team isolation. Then we get into parity drift. We can define now one state machine for one feature across both Android and iOS. In the same way that an API defines a contract between clients, this state machine definition is a feature level contract. It defines data, tasks, expected UI states, and so forth. So suppose a transporter finds themselves in some wild emergency situation, requiring them to shift entirely different devices. Maybe they personally use an Android phone or an iPhone, but they've been given the Android phone at the station. It breaks. They drop it on the ground, it breaks. And so now they pull out their own personal phone. They can log in, and they're not going to be shocked by the experience because the states are defined the same across the app. We've solved that parity drift. It's going to flow the exact same way. They can just seamlessly continue doing their work. And because the machines are self-contained with clearly defined inputs and outputs, they become eminently reusable. So for instance, if a team has released a feature that allows you to watch videos, and we'll talk about this here in a second, and you need to release a training video for a new market, for a new feature, what have you, you can just reuse their particular task handler. As long as you can pass in the right input, and then your code just needs to wait for its output, and it'll go do its own work. And so last thing here is you can also model state along with that, and we'll get into that. So a question I'm sure many people have is, all right, so there's other things out there like Android navigation or iOS storyboard, so why choose this over that? And it's because of that shared common language across the apps. That's one big thing. You don't have to, you may utilize storyboards or some navigation components, but on a higher level, you have one language that's going to be interpreted the same across the apps, regardless of the underlying actual work that is being done. And the language machine separation allows us to define the flow of a given feature also separately from the actual execution, which is really nice. And further, in addition to allowing us to define workflows in the app, it allows us to model state within the app as well. So let's jump into a couple of examples here. I want to express that none of the examples we're going to see and the code we're going to see here is actual code that's running in the Flex app itself. These are just naive examples that allow us to kind of just get an idea of what we're doing with the state machine, how we're going to utilize it, how you can model flow, et cetera, with it. And for the sake of this, we're just going to focus on a couple of different states. We're going to focus on like task states, choice states, and we'll define what these are, and then do a little bit in parameters there. There's a bunch of other stuff that you can do with these. We're not going to worry about that too much. So just a task state. What a task state does is it passes its input to a task handler. And this part right here, that's where you actually do your work as a developer. This is the place where your business logic sits. You're going to receive some input. You're going to do a particular set of work, wherever that is, and then you're going to push out some output. And this is all user-defined stuff. And a choice state is self-contained within the state machine itself. And it doesn't reach out to any code defined in a tasks handler or anything else like that. It just makes its decision within itself. And we'll look at one of those. And then we'll look at a little bit of parameterizing. All right, so let's look at this example here. So let's say we wanted to model, just a delivery cycle. So we want our driver to go on duty. They're going to drive to the warehouse, the station, wherever. They're going to pick up packages. They're going to drive to the customers. They're going to deliver the packages and finish the delivery here. So this first thing right here that we have is just the intro to the state machine and the first state. And we'll just go through this real quick and then show how we model the whole thing. So as you can see, it's formatted exactly like JSON. Throw this into a JSON beautifier. It'll fail because you're missing some closing brackets here, but you get the point. It's just, value or name and values, all strings all the way through. You got the start at here, which says go on duty. Start at is basically your int main. This is where, the state machine interpreter says, this is where I'm going to start. This is the first thing I'm going to execute. And then we go into our array of states, our list of state objects. And the first state you see is go on duty. That's our start at state that we said start here. The type is a task. That means there's a task handler somewhere that's going to do some work. This is going to be the work that's going to be done inside of Android, inside iOS. And then we have this resource that I said, unique go on duty ID. If you're familiar with AWS, if you've ever worked with an ANR, something that says, oh, you know what, we need some Lambda to do some work. Here's its unique ID. It's going to go do some work. Let's just pass it some data, and then it'll return to us. This is the unique ID for whatever particular task handler is going to execute the go on duty work. And then we have to tell it, well, where are you going to go next? When you're done with your work, what's your next step? That's the navigation state. What we don't see right here is inputs or outputs for right now. Short of actually saying, here's your input, here's your output, is that any data that flows is all the data that flows through. So whatever object is passed out of the go on duty state, that's what's going to be passed into the next state. And we'll get into clarifying that later. So this would just be our first thing, go on duty. What does that mean? Log in, et cetera, et cetera. The next two states we have here are both task states. We have a navigation state with some type of unique ID again right here. It's a task, some work's being done. Then we have our pickup packages. It's a task state as well, some unique ID. Then we go to our deliver choice. So 3 different types of tasks, each one with their own unique ID, which means they're doing their own unique work, passing some data back and forth, doing some work in the background. Now we get to this deliver choice. And this is the first kind of interesting different state that we get to. So here is it's no longer a task state. This is a choice state. And so that means this is going to retain its execution, its work, whatever it's doing, just entirely within the state machine itself, as opposed to going to something external, going to a task handler and doing some business logic there. In this case, once again, we don't have any parameters coming in, which means it's all of the information coming in. And it's going to make some type of choice based off of a variable called more packages. And if it's true, this is some type of Boolean variable. If it is true, then we're going to go ahead and the next thing we're going to do is deliver the package. If it's false, in this case, defined as just default, we could be explicit to say if it's false, but what if it doesn't even exist? Doesn't matter. If the default, there's no more packages, let's just end our trip. And so let's look at that. We've got our deliver package. It's a task state again. Its next state is deliver choice. So we're doing a loop now. When this deliver package is finished delivering whatever package, hopefully it's returning within the Boolean here. It's counting something down and saying, are there more packages? It's returning that to the deliver choice. And deliver choice is either going to go back to deliver package, or given that we're done with packages, we're going to the end trip. The end trip is some type of task again, has its own unique ID, and it doesn't have a next state. It's done. This is a complete state machine modeling what we have here on the left. One more interesting thing about this is within this navigation state and this deliver package. The names are different, but they share the same unique resource ID. And that's because while they're different states, that state name is just for the machine to know where to go next within this JSON object. But they're going to be executed by the same task handler. we could envision these, maybe these are both mapping and they map to a station, they map to a customer's house. In that case, the same task can do the same work. They just need to know the input, where's the station, where's the house. So here we see immediate reusing of a particular task. All right, let's go to one more example here. We've got our same state machine. We got our workflow. You're going on duty, you're driving to a station, you're picking up a package, you drive to customer, et cetera, et cetera. So let's suppose in this situation, we find that, our drivers are running into a unique issue and they need a little more training to know how to deal with streets that are changing. I don't know. They need a little more training. We want to now introduce a training step into this. So previously we had these particular 3 steps that we started off with. You had your go on duty, drive to get your packages, and then start your delivery. And we want to put in here this new step. So here where we have go on duty, instead of going immediately to drive and pick up your packages, we have a new choice. And this choice state says, hey, do you need training? Once again, it's a Boolean. If you need training, watch this training video. And then we have this watch training task. Now, these values hopefully are passed in after you go on duty, you've logged in, it grabs some information from the back end. It goes, have we trained this driver yet? Have we not? I don't know. If we haven't, let's go ahead and do it. If we haven't, we can skip this training video. Here's where things start getting really cool. Let's assume that this watch training task, as we described earlier, much earlier in the talk, let's assume that somebody's already created a watch video task that they're using for something else. If it's already extant within the app, then this portion right here where we add this in, because this is just JSON, we don't actually need to push out new code to the app. We can now deliver this particular JSON blob, this state machine, to the app from the back end. Perhaps we mark a certain set of customers in a certain region and go like, I want all these people to try out this training video. And we're gonna get some metrics off of it to see if it works. We just alter the state machine, push that down as you log in, and then that new state machine gets run by the state machine interpreter. And we've made no code changes, but we've fundamentally changed the flow of the app itself. And that's where we want to get to parameters. So no parameters are being sent in here except for all the parameters. So what you can do in that particular case is you can go ahead and define as a state machine owner, as the owner of this watch training task handler. Like as a team, I could keep that to myself and just that could be the side, but this could be very valuable for other teams. So what I'm going to do is say, listen, I expect to receive a movie URL. So you need to pass in to me a movie URL. And as long as it's at the first level and its name is movie URL, then I can execute that movie given that that URL actually exists, et cetera, et cetera. But now as a developer who isn't familiar with this, I can just look at this state machine, go, oh, these are the parameters you expect. I don't have to dig into your code. We can write comments on here. We can make this very clean. And now I can pass in the information you need. If I'm receiving that on login and it was in a different format, I can reformat that with a totally different type of state that's like a pass state and make sure that, hey, I had it named as movie string. Oh, that wasn't good. I'm actually going to now rename it movie URL and pass it to you in the way that you expect it. And that's where things start getting really cool. So I'd like to talk here about kind of, the integration choices we made. I'm going to see how fast I've been talking real quick. Cool. We still have plenty of time. I'll talk through this really, really fast, unfortunately. Here's the choices we made while we were integrating the Amazon States language into our app itself and why we made these particular choices. So first of all, I want to say that we're still integrating this into our apps. In the meantime, our apps continue to grow. They're growing across regions, they're growing across features and users. So we needed to be able to integrate these architectural changes, alongside and without inhibiting in any way the app's natural acceleration. So what does this mean? It needs to be able to move to a new architectural vision, ideally without sacrificing any of that vision, while respecting the current app's functionality as a whole. So that means It must work alongside extant code, currently existing code, without interrupting any current features that are working, or features that are coming in the pike, that were set up before we made these particular changes. And it needs to integrate without having to do, any large refactoring from a team who wants to start using this. And hopefully, and ideally, it should provide value to developers immediately. So here are the things we decided up front. Our machines are loaded at app startup from a state machine repository and loaded into the state machine interpreter and executor as needed at runtime. So where's this app repository? It's both on the back end and it's on the app itself. So you can imagine, like in our previous example, that flow that you saw there. Let's go back to that real quick. This guy here, maybe this one's just, in the app. Everybody has to do this flow, but we're going to push in this new repository. And if that works, if we really like it, maybe now we update the repo on the app itself to have this as a default, and then we can push other state machines down as need be as we go forward. Yeah, so one of the reasons you saw the training video one, but another great example of that is, imagine if we are doing mapping in India versus doing mapping in Japan versus doing mapping in the United States. So in India, you may not be driving directly to a customer's house. You may actually be driving to a shop that will hold things for the customer, or that now a local person will bring it to the customer, they'll come to it. And so and Japan's tiling is entirely different as well. So you can imagine we don't want to have this really big state machine that has just a multitude of choices that have to be changed for now we're working in Singapore, now we're working wherever. Instead, that's when we would deliver, right after you've signed in. Oh, you're in India, your locale is India. Here's the workflow for you that makes most sense for you. Whereas, people in the United States are going to get a different workflow rather than having an over-convoluted state machine. State machines themselves, the second bullet point here, are individuals are self-contained and hold no state outside their own execution. So there's no data permanence related to an individual machine. That's not to say we did away with data permanence, in general, like who's the person using the app, et cetera, or any type of databasing on the app. There's still a need for that. It's separate of the state machine. Is a machine itself doesn't contain any permanence outside of itself. That way a machine can do work, doesn't hold state, just passes out the information or expects a particular information, and that's it. This is the same with individual tasks within it. Those are all treated as pure functions. So input comes in, work is done. If task B is dependent on the work of task A, then task A needs to pass the right work in. Pure function, so you don't have to worry about any strange side effects of any work you're doing. And for the purposes here of Android, the way we've kind of just structured this is, we model each individual machine itself into a single activity with n fragments, depending on how much UI is necessary in a particular machine. But so one activity runs the entire state machine for a particular workflow. There may be multiple workflows in an app. And what's super cool about all this is the heavy lifting itself is done within a state machine interpreter and executor. So this is they know how to read the state machines. They know how to translate or transition between states. They're the ones passing the information, the data across. They know how to call the relevant task handlers defined by those unique IDs. So as a developer, as an individual developer within the Flex app, the vagaries of all this are abstracted away. I just need to define my state machines and define my task handlers, and I'll let the interpreter and the executor take care of the rest. And this goes back to that code visibility issue. So I only need to worry about establishing my state machine, defining my input and output, and the business logic within those task handlers. And the overhead to actually set this up is very, very limited. And we have some tools here too that allow you to do validation of your state machines. So AWS itself, if you go and look at the Amazon states language at AWS, you'll see, state machine validators. Is this good JSON? Do you have all the necessary things here? We're going to build out some other tools as well for kind of our unique purposes, and I'll talk about that in just a second. And the last really cool thing that this choice we made early on is, Amazon is a data driven company. Every feature we release is wrapped in its own series of metrics that allow us to analyze its effectiveness, triage any issues, all that type of stuff. So what we've done here is within the state machine interpreter and executors that we've woven, a subset of these metrics just directly into those machines itself. So, what state just ended, what's about to start, how long was a user on the previous state. So you can imagine there's this subset of metrics that are always interesting to have to know how users are interacting with an app. And we've built that directly into the metrics that now, or into the executor that now, you as a developer defining your own flow, you get that for free. It doesn't absolve you from adding the additional metrics specific to you, but now you have a lot less of those to worry about in general. And so brings me to my last slide, and that's like, the caveats about this and future work that we're doing. So this is all very fresh. We're just rolling this out right now. So given that, and as teams and team members multiply and people bring with them different levels of experience and approaches to coding, and to keep a continual high bar, we have to put mechanisms in place as guards. And so utilizing the Amazon states language is an example of one of these reinforcement mechanisms that, reduces greatly the risks of errancy. So, you may ask for example, what's to prevent a state machine from becoming too large or too complex? And so, that's one of that, we mentioned it earlier, we're working on internal enforcement tools. So this would go alongside that state machine validation. You can imagine a set of tools that can analyze a machine for structural integrity, or for the potentially for size or convolution. But, as far as what is too big or what's too complex, these are things we're still deciding, we're still working on. One of the elements of scale we called out earlier was the number of transactions per second a system is experiencing. So utilizing Amazon state language in our apps doesn't affect that. It will not reduce the number of transactions per second on a system. It has no effect in that way. But it also doesn't add any additional layer of bloat. So as as transactions per second increase, any sort of latency or slowdown that is inside of a system tends to become exposed and exaggerated at that point in time. So what we've found is, through our own metrics and testing, that the addition of the state machine interpreter and executor is not adding any additional lag or slowdown to the app. So it's a net win in the sense of it's not increasing or decreasing the effects of scale for transactions per second. Now, one of the bigger caveats here is there, to the best of my knowledge, as of yet, there isn't any sort of library out there for the interpretation of the Amazon states language, and in Android or iOS. So in our case, we wrote our own interpreter and executor. And, I could see this absolutely being a barrier to other parties. So we built our state machine interpreter and executor, as architectural infrastructure. So it has become one of the keystone components to the app itself. So what that done is, as we pointed out earlier, this has reduced the interdependence of code across teams, but it's also placed greater scrutiny on this one particular component. And so let's address that last point for a bit. So earlier we talked about scale in terms of a particular code utility's importance to a system or systems. In this case, the Amazon Flex app is key to delivering packages. So by reducing all of these other risks of scale that we talked about earlier, about visibility, code size, multiple teams, et cetera, by reducing those, we've now focused down to this one particular element, and this has become the keystone element. But by creating this singular infrastructure level component that drives the rest, we reduce the overall app instability in general while increasing scrutiny on this one component. And because our state machine interpreter and executor drive the rest of the app, now this code, this key infrastructural code, is managed by a singular team tasked with maintaining that quality. So that extra scrutiny on this app is a net stability win. Now it's their job. It's heavily tested. They have to maintain the quality because it's such a key infrastructure component, any failure that might be like wholly catastrophic to the app is going to be discovered in dev time. It's going to be discovered way earlier rather than going out to the world and being discovered in production. And then a couple of other just additional feature work things that we're doing, or future work that we're working on. At the moment, it's really trivial to call other task handlers. You saw that with the addition of the watch training video task. But there's probably a need, and you can imagine there being a need to pause a particular state machine itself in mid-execution to call an entirely different machine and then return to execution. So that's one thing that, looking into, working on. And then there's always this dream. This is the non-technical wizard dream that, say a product manager or just any other interested party that has the authority to do this could, maybe access a web-based UI and simply move components around and restructure an app as an experiment or for a new market or for a specific purpose, and just push down that set of state machines that can just restructure the app on the fly and have an entirely new experience for the developers, or not for the developers. It is a new experience for the developers, but for a particular set of drivers or a new market or what have you. So that's it. That's my talk on state machines, and thank you all for being here. And now I think we're going to have some questions come up. All right. Move this down. No questions. All right, folks. Thank you for your time.